Alright, so this is the third video for class 1, and we're going to do some examples now. These are ridiculously easy examples, so don't start thinking this class is going to be all that easy all the time. Right? But anyway, here's example 1.1 from the book. What is the weight of 1 kilogram mass at an altitude where the local acceleration of gravity is 9.75 meters per second squared? Well, we want to think of is sum of the forces equal to mass times acceleration. And these are vectors, actually. So the sum of the forces in the y direction, and we'll define the direction that we mean, is equal to mass times acceleration in the y direction. Well, the acceleration is gravity. This is actually a tough one to use. I really want to introduce my dynamics stuff, but you guys, at least at the University of Hartford, don't take dynamics until the next semester. But anyway, we can know that following this idea, the force is going to be mass times gravity. So the weight is mass times gravity, whereas that's the acceleration that we're referring to. But we don't really accelerate onto the thing in terms of weight, because most of the time it's just some kind of like stagnant thing, right? It's not accelerating in our perspective. It is accelerating towards the center of the Earth, but that's not. Yeah, I'm sorry. I'll stop from there. If the ground wasn't there, it would be accelerating, but it's statics as far as we're concerned. But anyway, so what we would do here is the weight of the thing is going to be the mass, or 1 kilogram, times 9.75 meters per second squared, right? So what you would think of is that you'd get 9.75 kilogram meter per second squared. Well, that's not the thing that we want to get. We use for forces, we use newtons in the SI unit. So what you find is that this thing right here, boop, turns into a newton. So the answer is 9.75 newtons. I think that's a better way than to try to think up a way, that sometimes they use like this conversion factor thingy, or to multiply by the thing. I just see anytime you see this collection of units, it turns into a newton. So here's your answer, and I prefer that you box your answers at the end. Here's another example where we're using English units to kind of compare and contrast what happens here with the 1 pound mass that's taking place. All right, so we once again have mass times gravity is equal to the weight of the thing. All right, so that's going to be 1 pound mass and times 32.0 feet per second squared. Right? But when you combine those two things together, they don't go bloop and turn into a pound force. You have to use 1 pound force divided by 32.174. So this is always a standard. It's not equal to whatever that local gravity happens to be. And then you have the pound mass foot on the top, second squared on the bottom, boom, right there. And now you get the bloop, 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 bloop. All right, resulting is going to be approximately 0.9946, and these are a pound force because we've multiplied it by this conversion. It's silly, but that's the mindset that will work out for you. Now, this could be your answer. But it's like we don't really need to use 4 sig figs for this. One method of thinking of this is that we were given this in only 3 sig figs, so we really give the answer in 4 sig figs doesn't make sense. But in general, it's totally okay with me to go 3 or 4 sig figs. I don't want to make a big deal. Haha, that's my name. Out of it. So that's a representative answer. Do we want to continue or make another video? Let's make another video. So, to be continued.